I often have students that get confused as to when you're doing gravitational potential energy, how do you know what to use, the universal gravitational potential energy or just MGH? Anytime that you're on planetary scales where your distance above the Earth is, we could set it pretty arbitrarily as more than 10,000 meters above the Earth's surface or, a couple thousand meters, you should probably use universal gravitation. But I want to show you that universal gravitation will work for any situation, even if we're really close to the Earth. And what I want to show you right now is that the change of gravitational potential energy for a 2-kilogram object lifted 3 meters off the surface of the Earth, that change in GPE will be the same whether we're using MGH or the universal gravitational equation. It will be the same. The change will be the same. Now, because we're right at the surface of the Earth, and we're assuming that lowercase g, that little g right there, doesn't change for this 3 meters that we're lifting this up, it's okay to use MGH because we're so close to the surface of the Earth, less than 3 meters away, but it's also okay to use this. You can use universal gravitation anytime. 100% of the time this will work. So I just want to show that. So let's go ahead and just use MGH. We're going to set, if we want to use MGH, you've got to set where you want UG equal to be 0. So let's set it, makes sense. If we're using this, we have to set it. And let's set it at the surface. So UG final is just MGH. And we got a 2-kilogram mass. We're using 9.8 for G. And let's lift it up 3 meters. So there is our change in gravitational potential energy. That is mg times delta H, 58.8 joules. Using universal gravitation, we have this. We've got, instead we have to use gravitational potential energy is negative gmm over r. It's negative, and you don't have a choice here. You have got to set gravitational potential energy equal to 0 at r equals infinity. If you're using this formulation, you do not have a choice. This only is true, and I'll prove this in another video, that UG equals 0 at r equals infinity. This is only true when that's true, when you set that equal to 0 there. So I've got to set it there. Well, what's the initial gravitational potential energy? After all, we're looking for our change. Well, we're starting off at the radius of the Earth. Just to review what we're doing here, we're starting this thing off right here. That's where it is right now. It's at r of the Earth. So let's go ahead and figure that out. It's negative g, negative big G, mass of the Earth, mass of the object over the radius of the Earth. Why don't we have to count the radius of this tiny object? It's only a 2-kilogram object. It is negligible compared to the radius of the Earth, which is like 5 or 6 times 10 to the 24, or sorry, 6 times 10 to the 6 meters. It's like 6 million meters there compared to like 1 meter. That's nothing. This radius of that thing is negligible. So when you calculate this, you get this number. It's negative. Gravitational potential energy is less than 0. That is what you get. Now, what is the gravitational potential energy final? Well, when I lift it up, what is it, 3 meters right here, lifting it up 3 meters, that'll be negative g times the mass of the Earth times the mass of our object over the radius of the Earth plus 3 meters. And when you do the math, you just do it with your calculator, you see this is the gravitational potential energy you get. And notice that look at the number. Now you're lifting it up, it should be a higher number, and this is, notice this is 1252889 and then 79. This is 125288920. Notice the difference between right there, right here, and right here. This, you say, wait a second, this is a lower number, but it's a lower negative number. This is closer to 0. This is lifted higher up. It's a smaller negative number. So this is really a higher gravitational potential energy than this. The difference between these is 59 joules. Notice that we changed our energy by 59 joules when we calculate it using universal gravitation. And it's also, the change in energy is also 59 joules when we calculate with MGH. We get the same change of GPE no matter which method we use. You can only use this if little g is unchanging. That means you're at your change in height is relatively small so that the acceleration due to gravity does not change.